Hello, and thank you everyone for attending the session. I'm going to present my recent study on probability biases in connection with the cooperation level in the prisoner dilemma game in an experimental study. In this research, I analyzed important features of human behavior and cooperation. The motivation for this comes from empirical observations that individually rational strategies can lead to collectively inefficient outcomes, particularly in social problems. Essentially, the conflict between social and individual incentives is a prominent feature in the social problems. This setting requires that players cooperate in order to obtain the social efficient outcome that benefits everyone, but it comes at the cost of foregoing individually rational outcome. Then in such scenario, the issue is what is the best way to sustain long-term cooperation when we consider social welfare? Let me motivate by starting with the following prisoner dilemma game, which also I have used in my experiment. There are two players and each have two actions, cooperation and defection, and defect is the dominant strategy. As you can imagine, defect is a unique equilibrium outcome shown in bold in a one-shot game. When players play this game, for fixed number of repetition, for example, t times, then defect is the equilibrium outcome once you use backward induction. What's interesting about this game is when the game played infinitely repeated, meaning that the game continues to the next round with some probability. In such setting, then cooperation can also be part of the equilibrium outcome if players are patient enough, meaning that if the player's discount factor delta is somewhat higher than some theoretical threshold like delta bar, then cooperation gives a higher expected utility to players compared with the case that the player decides to deviate from cooperation one round to obtain the outcome 90 and then 18 thereafter. So in this setting, in this game that you see here, delta bar is set to be equal to 0.11. For any discount factor above this threshold, then cooperation is part of the equilibrium outcome. Let's say that we have an outcome sequence for this game, x0 in the first round, x1 up to how many rounds the game is being played. And under discounted utility scenario, then the total utility is using the discount factor and the utility, which will be linear here. Then the point here is the delta here takes a dual interpretation. On the one hand, you can interpret it as time discounting, the discount factor that the player uses to evaluate outcome between rounds, and also it can be interpreted as the continuation probability, meaning that the probability that the game continues to the next round, which take us to think about a scenario in the framework of discounted expected utility. And this is an important consideration to have because joint cooperation is a socially desirable outcome, whereas defect is an individual rationality. What I do in this study essentially is looking at a separate treatment between continuation probability, which it can inherit probability biases, which I talk about it in a minute, and looking separately at discount factor here. Then let me talk about that probability and a particular probability bias that I'm referring to. More specifically, I refer to it as probabilistic risk attitudes as it's been introduced by Wacker in a 94 paper. On the x-axis are the probabilities between 0 and 1. And on the y-axis, there is a bias in the perception of these objective probabilities. For an expected utility subject, the relation between probability and the perception of the probability is a 45-degree line, meaning that there is no bias in the perception of the probability. Then once we allow for models other than expected utility, for instance, prospect theory, then we know that there is a bias in the perception of those probabilities. For example, just assume a functional form introduced by, for the probability weighting function introduced by Tversky and Kalman. Then you can think about the case that subjects or a decision maker is overestimating low probabilities and underestimating high, moderate to high probabilities. This is going to take the functional form for the probability weighting function is an inverse S shape, meaning that subjects are optimistic for low probabilities and pessimistic for moderate and high probabilities. Then also it can be the case that the probability weighting function takes a S-shaped form, meaning that subjects are pessimistic for low or even might be moderate probabilities, and they will be optimistic for high probabilities. In this study, I also elicit the probability weighting function or those probability bias at individual level. For the benefit of time, I just give you an overview of how many and percentage of subjects falling into one of each these categories. The method that I use to elicit probability weighting functions is based on Offerman and his co-authors paper in 2009. They use an incentive compatible quadratic scoring rule. And this model is, first of all, incentive compatible. And second of all, it is generalized to include non-expected utility models as well. And what I observe in the data is that 52% of subjects are expected utility subjects, meaning that once you consider probability weighting function of Tversky and Kalman, the coefficient gamma over here is equal to 1, meaning the 45-degree line on the graph. Then I observe that there are 21% of subjects who are inverse S subjects with a estimated coefficient gamma equal to B.7. And I observe that 26% of subjects are S-shaped subjects with the estimated coefficient gamma to be equal to 1.4. And this finding is very much similar and in line with the common findings in the literature of individual decision-making, for example, by Abdelou in 2000. And what is crucial and important here, and that is a point that I want you to take away from this slide, is in fact the existed heterogeneity in the data. So I have subjects who are expected utility subjects and some unexpected utility subjects. Then the question that I will be asked here is that given the dual interpretation of discount factor and the emerging literature on the interaction of time and risk, is there any scope to have a reinterpretation of cooperation and behavior in repeated games? And in an experimental study, I explore this relation between probability biases and the cooperation level. I can show that there is a relation between the curvature of the probability weighting function and the cooperation level, and it can be explained by Pahlavi's paper in 2008 using the impatient index. And the impatient index essentially is a relative weight across 2 time periods. And each time period includes a constant time discount factor and those probability biases. Let me just tell you about it a bit more formally. Consider the following deterministic outcome path. The decision maker obtains outcome x0 in the first time period, x1, so on and so forth. Then obtaining in this Pahlavi's framework, obtaining outcome xt is subject to a risk. For example, the decision maker doesn't reach to that particular time period, or the promise of obtaining that outcome is not kept. So there is some survival probability, let's say that it is 1 minus p. In this scenario, the decision maker has a pessimistic view about future outcomes. And it's worth mentioning that there is a more general framework considering time and risk developed by Pahlavi and his co-authors in 2002. But for now, I will be using his initial paper. Then the discounted expected utility in Pahlavi's paper is going to be include an additional factor, which is the bias in the perception of getting to that particular point, which has essentially a flavor of risk, and a time discount factor. So here are the two components in the discount factor, in the total discount factor. Then he introduces impatience at time t, which is the relative weight between discounting total discount at time t and the total discount at time t plus 1. Then the next consideration here is the impatience index. Essentially, in this framework, Halabi cares about how I0 is evaluated with respect to I in any other time periods. So this is a framework that I'm going to use in repeated game. Just a little bit of notation in repeated games. Consider a game, for example, the prisoner dilemma game that it was at the beginning of this session. There are n players, each have a set of action A, and they obtain a utility from payoffs. And then the infinitely repeated game, let it be gamma infinity, that continues to the next round with a probability P. That is the idea of infinitely repeated game. Then AIT is players I action at time T, and for all players, let AT to include that. Then both phase A includes action profile, all actions taken by all players throughout all time periods. Then I can construct players I total discounted prospectivity or total payoff in the following way. That the utility that the player obtains includes is discounted by two factors. One of them is a constant discount factor, and the other one is a probability weighting function, or those biases in the perception of probability, for which you can imagine the Konvan-Tversky type of probability weighting functions. Then the impatience, as has been introduced by Halabi, the relative weight of total discount at 2 time periods. What I use here is the idea of relative impatience index, meaning that I look at I0, the relative weight of outcome today versus the outcome tomorrow, to I1, which captures the relative discount between D1 and D2, like the outcome today and the outcome today versus outcome tomorrow, compared with the outcome tomorrow and the day after tomorrow, and I call it relative impatience index. Then you can show that for an expected utility subject, this relative impatience index is constant and it is equal to 1. So expected utility subjects are going to be the benchmark of comparison for me in this study. Then for inverse S players, the relative impatience index is greater than 1. Then the straightforward interpretation is that these subjects are patient subjects. And by theory, theoretically, we can predict that inverse S players, being more patient than the expected utility subjects, will be cooperating more than expected utility subjects. And this index is true for all continuation probabilities. Next is to consider S-shaped subjects. And for those subjects, I can show that the relative impatience index is smaller than 1. Meaning that these subjects are impatient subjects. And theoretically, the prediction is that S-shaped subjects cooperate less than expected utility subjects because they are just less patient than expected utility subjects for all continuation probabilities. Now, let me walk you through the experimental design. As I mentioned at the beginning, the experiment has 2 parts. In part 1 is the infinitely repeated game. In part 2 is the elicitation for those probability biases. But for today, for the benefit of time, I just focus on the game experiment design. In the game experiment, I have 5 different continuation probabilities, 2 in a low continuation probabilities, 1 in the middle range, and 2 probabilities in high range continuation probabilities. And also I have 3 design of prisoner dilemma game. And essentially the difference between each one of these games is the theoretical threshold for which cooperation is supported in the equilibrium. The game that I'm going to talk about today is where the theoretical discount factor is set to be equal to 0.11, but I have, for example, a PD 0.90, meaning that cooperation is not supported in any of these continuation probabilities. More specifically, subjects completed 5 practice tasks. These are unpaid tasks. And subject played only one version of the prisoner dilemma game, but for all continuation probabilities. And they repeated the same thing 3 times. And they played the first round of the game for sure. They knew that there is going to be a continuation probability, and they knew the value for the continuation probability. They played the first round with probability 1 for sure, like they faced the first round, but continuing to the next round is subject to that continuation probability. And their order of the probabilities are random, and the payment was based on total points obtained during the experiment. More about the subjects. 104 subjects participated in the experiment. The experiment was completed in last year, February 2019, at the University of Manchester. The total experiment, game and elicitation experiment, lasted for 75 minutes with an average payment of £16 and £4 plus £4 participation fee, and I used O3A to implement the experiment. Now, the overview of the result about game experiment. This is the data that I showed at the beginning. In the expected utility, subjects are comprising of more than 50%. And the same thing is true once I look at the other subsamples. So in each one of these subsamples, the distribution between inverse S expected utility and S-shape is more or less similar to the population. And what I present today is based on 35 subjects played prisoner dilemma for 2011 for 5 continuation probabilities, and they repeated the same thing 3 times. Let me first tell you about the observation about cooperation in prisoner dilemma game once we only look at expected utility subjects and their choice in the first round. Let me highlight why the first round only. As you know, it's a repeated game, and there are other influential factors that might affect the cooperation, the effective vision of the subject. So in order to minimize the dynamic effects inherited in repeated games, I look at the subject choices in the first round and recall that they played the first round and continuing to next round was subject to that probability. What I see for the expected utility subject, here, let me tell you about the graph. On the horizontal line, I have probabilities, 15%, 20%, up to high probabilities, and just for expected utility. And the height of each bar shows a percentage of subject who chose the action cooperation. And as the figure shows, expected utility subjects, the level of cooperation for the expected utility subjects is relatively constant, about 50% for all continuation probabilities. Next, I look at expected utility subject in a relative comparison with a non-expected utility subject, which I have 2 groups for them, inverse S subjects and S-shaped subjects. So on the horizontal line, you're gonna see the 3 types of subjects, inverse S, expected utility, and S-shape. And underneath that, I have the particular continuation probability. Just recall that from the model that inverse S subjects are more patient than the expected utility subject. And the prediction is that they will be cooperating more than expected utility subjects. And this is true once I look at low continuation probability, for instance, and comparing the 2 groups. And recall that S-shaped subjects are less patient than expected utility subject. And the result that I get is in line with confirms the prediction that S-shaped subjects are cooperating less than expected utility subjects. And once I look at all other continuation probabilities, 0.2, 0.60 and 0.80, the similar pattern follows. So the main result is that probability biases plays a role in cooperation as predicted by the impatient index in a way that inverse subject cooperate more than expected utility subject and S-shaped subject cooperate less than expected utility subject. So essentially, this prediction is particularly true once we look at the relative impatient index and when it is extended beyond just a convex probability weighting function. Regarding the other two games, for some continuation probabilities, I can observe a similar pattern in terms of the level of cooperation, but it is not as prominent as it is in this game. Can I ask?
2 minutes or so, okay?
Okay, that was my question. Great. Then I just briefly tell you about where my study fits in the literature. So there are huge studies about infinitely repeated prisoner dilemma game. What is particular feature in these experimental and theoretical studies is that they use the idea of dual interpretation of discount factor as a probability biases and discount factor. And there are some studies, some empirical studies trying to introduce time preferences in games. For instance, obtaining an outcome in the next round is delayed by a month, by a week, by a month, so on and so forth, just trying to replicate whether or not there is any time inconsistency. And other studies looking at continuous time or even thinking about hyperbolic discounting. Where my study is different from all these studies has been done in the literature is I'm looking at cooperation from a different channel, which is those probability biases. And that is essentially inspired, motivated by many studies in talking about interaction of time and risk in individual decision making. And with that, I conclude my talk and looking forward for your questions and comments.